Okay, so let's get rolling. So we're gonna start by introducing ARM architecture, and then I think we're gonna end up skimming through several slides in the middle because we've kind of already talked about that stuff. We're going a little bit out of order, but we'll as we go. All right, hold on, let me get one sip of coffee in. All right. So we're starting to talk about the actual ARM architecture. Now, think about ARM as a more generic form of, let's call it, mobile computer architecture. ARM is a type of RISC, reduced instruction set process architecture that was introduced years and years and years and years ago. In fact, old Macs used to run PowerPC processors, which were a RISC architecture. And some of the older processor architectures also were reduced instruction set. The issue was that, so the idea was a reduced instruction set, which effectively means there are smaller number of magic tricks, fewer magic tricks, as I've described processors having lots of magic tricks. The fewer magic tricks you have, the less energy the processor is going to use, less heat the processor is going to give off, those kinds of things. And on a desktop type computer, while those things might sound nice, those aren't the highest priority things in the world. You know, from a heat perspective, you can put a bigger heat sink and fan on it. And from a power perspective, you got the thing plugged into the wall. Who cares? So all those things kind of add up to maybe that processor not being as kind of keeping up with the Joneses, with the Intel processors that were coming out that were based on an open architecture that tried to squeeze as many features as they possibly could into the chip. Well, now we fast forward a whole bunch of years and we're thinking about mobile specifically, and now heat and power reduction and all these things actually start making a lot more sense and are a lot more necessary. Hence kind of the strong comeback of ARM architecture. So ARM is, well, the comeback of reduced instruction set architecture, ARM being an example of that. Okay, so when we talk about really any processor, but we're talking about specifically mobile processors here, we're going to have multiple registers that are going to be available to us, and we'll look at those here in a few minutes. Several slides down, we introduced the ARM registers. We talked about these guys last time. So these are containers. We looked at them as bit by bit containers that you can store stuff in. You can store bits in these containers. So last time I tried to emphasize this idea of that a single container doesn't necessarily have to hold a single value. You can stuff multiple values in those containers and then pull them out in interesting ways using our bitwise operators and that kind of stuff. So all that's, I don't know, exciting stuff, whatever. But, you know, the point is that from an architecture perspective, we are introducing the tool that's there, and then we'll talk about how we can maybe use that tool to do some different things. So we're going to have a whole bunch of different registers as part of the processor. Some of them might be specially designed registers for jumps are going to be related to like if statements, and flags are going to be related to, well, I guess a bunch of different stuff. So we do have some general purpose registers, and then we have some special purpose registers. But anyway you cut it, our ARM architecture has these hardware registers just like Intel and other CPU architectures do. All right, so we do have 64-bit registers available to us, as well as 32 and 16 and 8. As we saw last time, we can use subsets of a register. Let's see. So Another thing that the modern day ARM architecture has built into it is a hardware-based virtual machine that allows your applications to kind of run in a separate little pod relative to other applications. So if anything goes wrong with a running application, it doesn't really impact the rest of the applications on your running computer, where our computer is our smartphone or something like that, which could then have, wreak havoc on battery life. All right, so our processors have at the hardware level evolved to protect us, protect the software developers from each other. Let's see. This is what I just talked about. All right, so cache memory. This is kind of interesting. So I mentioned before that the closer memory is to the actual core of the processor, the smaller yet faster it tends to be. So we've talked about hardware registers as kind of our top tier, fastest speed memory, let's say, but they're also going to be very small. They're either 8, 16, 32, 64 bits. Tiny, relatively speaking. Well, as we move further away from the processor, we're still sitting very close to the processor. We look at these various cache memories. So cache memories are going to be slower than hardware registers, but larger in capacity, yet faster than our system memory and smaller in capacity. The Snapdragon, which I mentioned, is kind of most of our Android devices have Snapdragon processors in them. That has all three, L1, L2, and L3 cache. Now, L1 and L2 cache are two different levels. Think of it as two different distances away from the processor for our discussion. But those are used by a single core of the processor. Whereas, excuse me, whereas L3 cache is sitting a little bit further away from the core processor, yet it is used to share information between multiple cores of the same processor. Okay, we'll talk a little bit about that as well. All right, so again, it doesn't matter whether you want to think about these things as better or worse or whatever. You just want to think about like, okay, here's the processor I'm dealing with. What are the features of that processor? And how can I take advantage of my knowledge of those different things to solve problems? That's the punchline. Whenever you have a tool and the tool has a whole bunch of features, you say, oh yeah, the microwave has this special button on it, has this other button on it, has all these bells and whistles. And many times, how many of you have kitchen appliances or something like that have all these fancy settings and you never use them? You typically stick to the core functionality of the thing, and there's buttons that you never even pushed. Processors are going to be very similar. They might have all of these interesting bells and whistles, but some of them might not be as useful as they might seem. Just because something has a feature doesn't mean you'll ever use that feature. All right. So Snapdragon chips have L1, L2, and 3 cache. Apple's AX chips only use L3 cache for sharing between cores. Otherwise, they rely on just the registers and the system memory for information moving between the processors. Moving between individual cores. Number of cores, we've already talked about this a little bit. We were looking at those pictures several classes ago. So the modern Snapdragon processors have 8 cores. And this changes from year to year. So, it's possible that the latest, greatest, these numbers change just tiny bit, but this tends to be the mindset of the processor right now. So Snapdragon has 8 cores, 1 high performance, 3 medium performance, and 4 efficiency cores. So they've broken it down a little bit more granularly than Apple has. So they've said, okay, we're going to give you 1 core for the highest performance stuff. You're running a game, something like that. We're going to give you 3 cores that are somewhere in the middle, using less electricity, giving off less heat than the high performance core, but still more powerful than your efficiency cores. And then we're going to give you 4 cores for kind of doing everything else. small system tasks that don't rely on maximum speed, all sorts of stuff like that. Oh my gosh, I gotta wake up. iOS, really, we're talking about the AX chips. These guys have 6 cores. I think as we see them evolve, we're going to see more cores, but this is their rough mentality. So they give you a couple of high performance cores and then the rest in lower performance, less battery, slower, yada, yada, yada cores. All right, so what we're looking at here is the kind of the mindset of the architecture for mobile devices today. So you're seeing written all over this decisions that give you the flexibility of running higher performance applications when you need to, along with the capability of running in a lower powered mode for the rest of the time. And really, when you think about this, just think about the way you use your smartphone. And really, every year we probably use our smartphone for a little bit more productivity than we did the year before. In the early days, it was a phone that you can also check email on, something like that. And now, at least the way I think about my smartphone is the fact that it's a phone is really not that important. If I couldn't make calls on it, I wouldn't be all that upset is the punchline. I use it for, watching a lot of videos. I use it for doing email, texting, all sorts of messenger type stuff. I use it for doing spreadsheet type stuff. I use it for grading. I do all sorts of things from my smartphone, and that it starts becoming more and more and more of a productivity tool, which is we're going to start thinking about it more and more and more like our desktop computers or our laptop computers that make less of these trade-offs at the processor level. Although we're seeing, we mentioned earlier that Apple is now, they have an ARM-based architecture with their M1 processor line that they're putting in their laptops and actually going to start putting in their desktops, although desktops are sort of kind of going away. These guys are moving towards ARM architectures as well. But what you'll see is when you look at the difference, I think we looked at a picture of it, of like the M1 Max processor. If you look at that versus like one of Apple's AX chips, or even you look at that versus Apple's original M1 processor, which they did put inside of an iPad, what you're seeing is less concern for that battery life and power consumption type thing, and heat dissipation type thing. Not that there's no concern there, because really when you think about what Apple makes smartphones, tablets, and laptops. They have a couple of other devices there, but those aren't really nearly as popular as what we just discussed, as what we just said. Sure, iMacs are still floating around out there, but they're far less interesting to people. They're far less common than seeing somebody running around with a Apple laptop or an iPad or an iPhone, something like that. Similarly, just recently, Apple released their an updated kind of version of the Mac Mini. I think we looked at a picture of that thing with their what was the M1 Ultra processor, which was 2 M1 Maxes just kind of laid next to each other and then soldered together. Well, okay, so still that's moving closer and closer to mobile. We haven't seen them upgrade the Mac Pro in a long time. Really, they're becoming more and more of a mobile company. Let's see here. So we've discussed this before. Why have multiple cores at all? Where we just mentioned these two different approaches, the two different competitors for mobile processors, both having kind of, 6 to 8 cores. And, that means for each core, you can do, more than one thing at once. So we ask ourselves, well, when would it be helpful to do more than one thing at once? And going to real life, there's plenty of tasks that, I think I probably mentioned something like shoveling snow. If you have 7 people helping you shovel snow, you're going to shovel the snow quicker. than if you just have one person out there doing it. Whereas, you know, the proverbial example of how many people does it take to change a light bulb? Those are tasks that don't necessarily benefit from having multiple cores. All right. But with mobile, we've taken that to one level further by saying, okay, well, can we do all cores need to be created equal? You know, do we need to create the fastest, you know, Intel Core i7 processor and then just duplicate that core 6 times? Or can we have a processor that then has multiple cores, but they're not all created equal? Some use less electricity, perform at a slower rate, but still are perfectly acceptable for certain problems. All right, so multiple cores, again, from the processor as a tool perspective, give us the flexibility for doing more than one thing at once, and we can choose what kind of core we want to use for those types of things. Okay, we've talked about iOS stuff, we've talked about Android stuff. We talked about this last time. I think I have a picture in here that tells the kind of the punchline for the octal versus hexadecimal number system. You know, why are these other bases interesting? So first of all, here's the octal number system. For octets, these are the 8 unique states that 3 bits can be fully described with. So using exactly 3 bits, I can show 8 unique states. And it just so happens that for octal, you have 8 unique octets digits, if you want to think of it like that, to make up octal numbers. You have 0 through 7. So with exactly 3 bits, we get to fully use the bit space, we can represent all of the octets. Similarly, with 4 bits, we can represent all of the hextets, no more, no less. So we're using the full 4-bit space. So, you know, you know, so we're saying right now the popular bases with computers are decimal because people are involved, binary because digital logic's involved, and then octal and hexadecimal because they have this very compatible relationship with the binary with 3 and 4 bits. Using octal or hexadecimal values allows us to store larger magnitude values in kind of a smaller footprint. And then we can translate back to what we need it to be later on. Okay. So if octal is 3 bits, hexadecimal is 4 bits, the next popular one is probably going to be 5 bits, which is base 32. So if our amount of memory and things like that keeps getting bigger and bigger and bigger, and we actually need to represent, we're going to kind of talk about the hexadecimal values here in a second. We need to represent those things in you know, more concise footprints, then we might go up to a base 32, but I don't think we're quite ready for that at this point. All right, so that's the base 32. All right, so this comes down to why do we want to use hexadecimal? What's our end game for hexadecimal? Where we most commonly see it is when we're dealing with computer memory. So we're still talking about our architecture here. We have our processor and the processor's relationship with the CPU memory. So what sits between our processor and the system's memory is the hardware registers, then L1, L2, L3 cache, and then we have our system memory. Well, even if we're dealing with L1, L2, L3 cache, what I'm about to describe still makes sense, but it's the most obvious example when we talk about it with system memory. So in your modern computer, you have, you know, 8, 16, 32, 64 gigabytes of RAM that comes with your computer. So, you know, the higher end computers today have 64 gigabytes of RAM. There's servers and stuff like that go up to 2 terabytes of RAM. But for consumer computers, you're probably looking at 16 to 32 gigabytes are fairly common, with 8 on the budget pleaser machines and maybe 64 on the super high-end gaming machines. All right, so with 64 gigabytes of memory, we want to think about, well, how do we address that? How do we, when we say address something, we're really saying, how do you uniquely describe one place in memory from another place in memory? All right, and I like to think about this thing like our houses. Okay, so how do you, if you know you live in a neighborhood and you need to tell somebody where your house is, and you want to make sure they arrive at your house and not your neighbor's house, we have an address, right? You know, 123 Elm Street, something like that. You give them a zip code, all this stuff. So human beings' version of addresses are pretty complex, right? We have a house number, we have a street name, we have a city name, we have a zip code, we have a state, we have a country. You know, we have lots of things that kind of zero you in as to exactly where that place in memory is when we deal with our addresses for our houses. Well, in our computer, the way you want to think about system memory is if it's this big one single long street. All right. And so if we have, I use an example here of Ubuntu 64-bit Linux, where it supports 48-bit addresses because it uses some addressing for just the system itself. All right, so effectively, when we say something has a 64-bit operating system, typically that means that it's using something along the lines of 64 bits for its various operating system features. One of the operating system features is memory management, and Ubuntu uses for user level memory 48-bit memory addresses. All right, well, what does that mean to us? That means that we have 2 to the 48th power unique places in memory. 2 to the 48th. So that is a, oh man, what is that? That's thousands, millions, billions, 281 trillion, 474 billion, 976 million, 710,656. Okay, so 281.5 trillion ish, 281.5 trillion unique places in memory that Ubuntu, 64-bit Ubuntu Linux is able to deal with. All right. So, you know, depending on the operating system, they might decide that, you know, how big is each house? If we're keeping this with our analogy of our, you know, the houses on a street, you know, are all the houses those mini homes, the tiny homes that you see on TV, or are all of them mansions? Okay, so obviously the street addresses stay the same, but if you have 100 houses that are all tiny homes, your total number of square feet is going to be a lot smaller than if you have 100 mansions, even though they might all have the same, you have the same physical number of memory addresses. 100, we had 100 unique things we were addressing. All right, so depending on the operating system, they might flex in terms of how much stuff do you want to allow there to be in a single location in memory. How big is the house? All right, and you know, the same decisions go into computers as go into real life. You know, we might, you know, your initial human thing, well, the bigger the house, the better. Okay, well, is that always true? You know, if you think about your system memory, what kinds of things are you storing in system memory? Usually it's going to be things like numbers or, you know, representations of characters, or maybe 8-bit chunks representing a single byte that's part of a software application or a video or something like that. All right. So if you have 128-bit size houses, and you rarely store 128 bits in there, you're wasting a whole lot of space. Just like I suspect if you have 100 mansions next to each other, a lot of times just super rich people buy the mansions and, you know, they're not taking up all the space inside that mansion. It's more of a show off type thing. Just as an example, I like to compare things from, you know, really technical low level hardware to real life, and the stuff is real. You know, you can have a mansion that takes up more space, but we're still only giving it one address. It has one street address for that mansion, and the amount of stuff it can hold is significantly greater than the smaller house 2 doors down. which also uses up one memory address. So typically in a computer, all houses are created equal. So whatever the operating system dictates the size of the house is, that's how much individual memory can live at a single address. But what we care about here in this course is the addressing themselves. All right, so we have whatever I said it was, 281.5 trillion houses that we can have inside of our computer. You know, so that means we have 2 to the 48th power unique houses that we're allowed to have. And we're going to make the assumption that every one of those houses can hold the same amount of stuff. And that amount of stuff, if it's 8 bits, so if we take our 2 to the 48th power, and we assume that that is, we assume that each house is a tiny home and it's 8 bits. So, you know, we'll call that, so 1 byte of memory per, which is the worst case scenario, which most operating systems use more than that. But let's just look at this as a worst case scenario. So every one of those addresses holds exactly 1 byte. So that's the number of bytes that exist. So we divide that by 1024. That's kilobytes divided by 1024. That's megabytes divided by 1024. That is gigabytes. So that means that the theoretical maximum amount of memory that Ubuntu Linux can address. You might have other limitations that make the maximum amount of memory less, but you can have 262,144 gigabytes of memory that we have unique memory addresses for. Yeah, it sounds pretty good. There's all sorts of other limitations that go into that, deciding how we're going to use it, but that's the number of actually, let me make sure I'm telling you that right. That's unique spaces. That's the total bits that we have. So we have 262,000. That's actual. Give me 1 second to think about this. Unique addresses. We're going to have 8 bits per address. So that's the total number of, or 8, yeah, so 1 byte per address. Yeah, so this is the total number of gigabytes that we can theoretically uniquely identify in 8-bit chunks. Unimportant operating system, type thing. Here's another example of, if we have 4 bytes instead of 1 byte, you have 1,024 terabytes of technically supported amount of memory, something like that. Again, not that important for us. This is just a math problem. Okay, for us, we want to think about the memory addresses as, why do we use hexadecimal? We use hexadecimal because we can represent a really big, house 229 trillion. Instead of this giant number, we can squeeze it down into a smaller footprint by representing that decimal number in hexadecimal. Or actually, even worse, when you're dealing with computers, you're going to be representing that gigantic binary number in a much smaller package, which is going to be in a 16-bit or a base 16 number. So it really comes down to the convenience of number representation with the we'll just call it convenience on both sides. Convenience of number representation with the convenience of getting it back into binary. That's the kicker. Okay, because at the end of the day, if you're on a computer, it has to be binary. It's got to be able to deal with it in binary, and it has to do that fast. All right, and we can map from octal or hexadecimal back to binary very, very, very quickly. We don't have to do a whole lot of math to make that happen. The key doesn't work anymore. Did I hit something? That's interesting. All right. We already did that. We've been talking about that. I'm talking about this. Just talked about that. Let me talk about this for just a minute. I don't want to get too deep into it. It's kind of the same argument we just talked, but it's relative to another class you'll take, the 540 class. So when we deal with computer network, I know several of you actually already had the class, but we have this thing called an IP address. And you can really, and the fact it has the word address in the end of it, you can think of an IP address as similar to a memory address, but instead of uniquely identifying a single place in computer memory, you're uniquely identifying a computer that lives on a network, whether it's the internet or a local area network. It's a unique way of representing that. Well, the IPv4 version of IP addresses used a smaller number of bits to represent the unique address, which then means that you have a fewer number of total unique devices that can be on a network at once. Now, maybe in the early days, they assumed that was plenty, but now, because in the early days of computer networking, every single computer that was on the computer network was a desktop computer. Well, then we started letting laptop computers sneak in, and then we start having, now we have smartphones and we have smart devices inside your house. If you have a one of the Echoes or any of those things, those are all going to have IP addresses. Inside of your house, you have all these different devices that are uniquely identified on your computer network, your smart TVs, all that stuff. And now we have all the Internet of Things stuff, the IoT stuff, where you have smart light switches and plugs and things like that. I mean, we have a fish tank, 2 fish tanks actually that are on that each have an IP address because of when the lights are gonna come on with electricity and that kind of stuff. So the idea is that the number of IP addresses, number of unique places in memory that we need to represent is going up. So we're going to move from a IPv4 standard, which uses a smaller number of bits, to an IPv6 standard, which uses a larger number of bits, which is going to give us more and more the ability to uniquely identify more devices on a network. So it's the exact same argument as we're dealing with memory, except now we're dealing with uniquely identifying computers on a network. Common use for octal, you probably saw this when you did your paper, was file permissions in Unix. That's commonly used for 3 bits for octal, because you can, with those 3 bits, we're not using it for magnitude. We're not trying to get, oh, what's the decimal version of this? You're saying, okay, I have 3 bits here. Well, maybe 1 bit is whether or not something is read or write. Is read. The next one is write. The next one is execute. So with 3 bits, you can represent whether something is read, write, or execute just using single bits, single switches in there. Similarly, with the same 3 bits, you can use it for read, write, or execute for 3 different groups. So in Unix, out of the 3 bits, it's the user, so it's the owner of the file, the group that the owner's in, and then everyone else. So that's what those 3 bits have, and depending on what the number is in that bit between 0 and 7, that dictates whether it's read only, read write and execute, that type of thing. So what I want to push there is we're not using it to hold a value. We're not going to say, oh, okay, well, it's 755 is the permission for this file. We're not going to convert 755 into its number, into the decimal equivalent. That's not important to us. Instead, we're using those 3 bits to hold information that has other meaning that we're probably not going to do math with, but it still has meaning. Okay, so this gets back to this idea that we have a set of tools laying in front of us, and how we choose to use our human intelligence to use those tools, that's where the magic comes in. It's not all about holding numbers, even though that at a glance, that's all we're doing is holding binary numbers. Sometimes you want to do math with the numbers. Sometimes you want to store other meanings. And we kind of saw that last time with the bitwise operators where we were storing multiple numbers, but we don't have to choose those to use those as numbers that are going to be, you know, I don't know, mathable or however you want to talk about it. It's really weird that I wonder what did I click? Let me reopen Keynote real quick. My arrow keys no longer worked. There we go, back in business. All right, so we talked about this. I don't really want to talk about this very much. This just comes down to how do we actually store larger values? Do we put the most significant digit to the left or the most significant digit to the right? That decision comes down to how do you perform different operations on a number and whether or not you have to reverse numbers or not. Doesn't matter for us really. This is kind of what I've been talking about, the why of all this stuff. We have resources, use those resources in interesting ways, even if it wasn't necessarily the way that that resource was intended to be used. Okay, so now we're kind of, you know, have our re-intro because we're getting ready to talk about assembly here. So kind of a programming language. How do human beings solve problems? We need to remember stuff, ask questions, repetition. Well, we've been talking about remembering stuff for a little bit now with all these hardware registers and bits and bytes and all that stuff. All right. Well, now we need to add some additional logical abilities in there for asking questions, repetition, doing some mathy stuff, whatever. Okay. You know, and just kind of finishing up these two slides because I mean they're in all my classes multiple times. Just to reiterate it, you know, so programming languages have this mapping. Memory is usually represented through something like variables. Asking questions is through conditionals. Repetition is through loops, functions, you know, similar things. But the important thing for us is that 100% of programming languages have facilities for these three things. That's whether we're dealing with a high level language like Java, C++, whatever, or we're dealing with a low level language like we're about to look at in here with assembly. So high level languages have a one to many relationship with the CPU. You write one line of code in Java, it translates into a whole bunch of magic tricks on the CPU. Whereas a low level language like assembly, we write one line of code in assembly and it translates into exactly one magic trick on the CPU, one instruction on the CPU. So it feels a whole lot less powerful because you're, you know, when you cast your spell, it's not doing nearly as much as a single line does in a high level language, but you're getting to play around with that granular control of those magic tricks, which is important to us in here. It's not that you're going to go out into industry and write a whole lot of assembly code, but really what you're doing is you're understanding what your high level code ultimately turns into before it runs on the CPU. So understanding like what does an if statement actually look like at the assembly level? What does loading and storing things? What does putting something into a variable actually look like at the assembly level? What does a loop look like at the assembly level? Because those things are being created for us by a power tool like a compiler, which takes your Java program, you compile it, it turns it into a bunch of Java bytecode, which is a low-level language similar to what we're going to be looking at our ARM assembly here. And it's going to, if you have a simple program, it's going to turn into a whole bunch of lines of assembly code that accomplish some task. And we want to have an appreciation for that task. All right, we've pretty much already talked about that stuff, kind of the history of the Apple processors. We did talk about Apple's transition from, I mentioned PowerPC earlier today, but they went from PowerPC to Intel. And then what was funny about that is they then went, let's see, they went from Mac OS 9 to Mac OS X, which was a Unix based. So that made all the software that worked yesterday not work today, because now they're your very first paper in this class was, why does a compiler need to target both an architecture and a operating system? Well, so all the programs from OS 9 were targeting the PowerPC architecture and the OS 9 operating system. The very next day when OS X comes out, none of those programs work. Why? Because they were compiled to target PowerPC architecture, which is still what you have, but the OS 9 operating system instead of the OS X operating system, which is a whole different set of system calls, since it was based on Unix. So after they had that time period of letting the software providers catch up and recreate their software for OS X running on PowerPC, then Apple throws them a curveball again by switching from PowerPC to Intel. They flipped the other coin. So now, yesterday, your software that was written for OS X on PowerPC now won't work on your computer that's running OS X on Intel. So they have to be redone again. Not necessarily completely rewritten, but at least recompiled, probably some tweaks made. Usually we would call that porting. They had to be ported over. So they had to be recompiled at some level to go to now work for Intel on OS X. Well, now Apple's twisted the thing again. And now they've said, okay, well, we're going to stick with OS X, but now we're going to another ARM architecture, our M1 processors. So all the software that's running on the Mac I'm on right now, I'm running the Keynote's probably already converted over, but let's say like Chrome. So here's the Chrome web browser. Chances are this version of Chrome is targeting the Mac OS X, so the right operating system I'm running, but it's probably targeting the Intel architecture, even though I'm not running an Intel architecture. But what did Apple do in this particular case? They have a piece of software called Rosetta, which does real-time translation between the two. You're probably giving up a little bit of performance there, but at least from a user's perspective, all my software didn't stop working. So kind of a interesting history of stuff there. Okay, so getting into our ARM architecture stuff, and we're going to look at this right column here. All right, so we have registers. We've talked about registers a whole bunch. So ARM processors have 16 32-bit registers. These guys are named R0 through R15, register 0 through register 15. So that means we have 16 registers that each can hold 32 bits of data. What those bits are used for is up to you. We saw you have all sorts of bitwise operations. You can do interesting stuff with them last time, but they can hold a maximum value of 32 bits in there. So that's plus or minus 2.1 billion or up to 4.2 billion if you hold unsigned numbers. Okay, let's see. Then they've listed that a couple of these registers have special purposes. So the last three are usually reserved for special purposes. R13 is used as the stack pointer. So most processors, when you're from a problem solving perspective, they have a stack. A lot of times the stack actually lives in maybe one of the caches or system memory, but you need a pointer to get to it. So the stack is like a convenient way of getting a number out of a register without putting it back into system memory so that you can quickly get it back into the register. It's kind of a problem solving tool. So R13 will hold a way to get to that stack. R14 is the link register, indicating where to return from a function. So when you do a jump in your ARM program, when you go from line 14 to line 68 or something like that to go do something else, the link register allows you to quickly jump back and pick up where you left off. rather than having to store that somewhere else. So it allows for that, return from where you to where you used to be. Let's see, R15 is the program counter. So this is what's the next line of code that needs to be fed to the processor. All right, so the rest of those, so you can think of the program counter as like, if we think of our CPU as eating ARM instructions, the program counter keeps track of what's the next instruction we're going to feed the CPU. So the rest of those are free for us to use to store anything that we want. So there's a few conventions. So this is not a requirement, but a few ways that these guys are typically used. So the first four, R0, R1, R2, R3 are for arguments. And I think we did look at, we looked at hello world in Linux assembly, did we not? Can somebody remind me if I actually went through the an assembly program for Linux? I think it's in my slide somewhere. Nobody can tell me if we did that.
You did do, go back down, because you did do those like blue boxes right there. Up, there we go.
Oh yeah, I'm all I'm asking about is whether or not I walked you through the hello world program for in Linux assembly.
Oh, no, you didn't.
Okay, well, let me do that real quick, because that's directly related to what it's talking about right here with this, the first four registers, R0 to R3, being used for arguments. And maybe once I start doing it, you'll remember, because I really would have thought I had done this. Linux, hello world assembly, because this would have been related to the conversation about why do we need to target both the why do we need to target both the operating system and the architecture? All right, so this is not ARM assembly. This is i386 Intel based assembly. Still an assembly language, still low level. Every line of code here translates into an exactly one instruction on the CPU. Now, just as we just saw in here, the first four registers, this is a convention typically used, not a requirement, but a convention the operating systems will take advantage of. The first four registers, R0 to R3, are arguments, are for holding arguments. And we actually see that same pattern here in Intel-based architecture, where for hello world, I'm going to remember a couple things. I'm remembering the pointer to my string hello world. I'm also remembering how long that guy is. So just I'm remembering two things. But these first four lines are us using the first four registers in Intel-based assembly to pass some parameters. So I'm going to move into EDX, the length of my string. I'm going to move into ECX, the pointer to the beginning of the string. I'm going to move into EBX, just the number one. Well, what's the number one stand for? It stands for where I want to write it out to. Because the goal of this program is to display hello world to the screen. So I want to display it to the screen, which is standard output. And then EAX is going to hold the number 4, and 4 corresponds to the system call on the operating system. Okay, so effectively what I've done here is I've just loaded 4 different values, seemingly for no good reason, into these 4 different registers. Just like the first 4 registers, R0 through R3, are for arguments, kind of being passed to functions. All right, so then what do? I call upon the operating system, the kernel, and that guy goes, and what he's immediately going to do, because he's taking advantage of that convention that those first 4 registers are used for passing parameters, he's going to go and look at the very first register and see, oh, well, what do you want to do? Oh, you want to do assist write. Because the operating system has a system call called syswrite in Linux. And syswrite's going to say, okay, well, you want to do a syswrite, I'm going to need 3 pieces of information from you. I need to know what you're writing, how long it is, and where do you want me to write it to? And it just so happens that it's expecting in the second register to have some indication of where you're going to write it to. The third register, it wants a pointer to the beginning of the thing you want to write. And in the fourth register, it wants to know how many characters does it have to walk from that base address until it has covered everything you want to have written. So hello world is, I don't know, what is that? 5, 6, 7, 13 characters, something like that. So we're effectively saying I want to syswrite to the screen from the beginning of hello world, which is the H, and I want to do that. I want to walk 13 spaces from there to get all the characters I want to write. So this is us staging 4 values that will act as the parameter to this system call at the kernel. Well, this system call for the kernel. These are the actual parameters. All right, so we're seeing that same pattern from Intel-based assembly. So it's like, hey, this kind of works. You know, we're going to say that those first 4 registers, R0 to R3, are used for parameters to our system calls from the operating system, which then says that if you're an operating system writer, you're probably going to want to write your system calls so that they don't take more than 3 parameters, because we only have 3 extra parameters to work with. The first one is the kernel is going to look at what do you want to do, and then it's going to call one of its system calls that has 3 parameters. That doesn't mean it can't have more than 3, but then you have to start going outside of those first 4 registers, which are kind of conventionally used for holding those parameters. That's those function parameters. Windows-based assembly actually often uses the stack to hold parameters instead of individual registers. So kind of another cool thing. And then these guys, well, it says clobbered by the called function. So the idea is that once the operating system takes over and it says, oh, you want to call this function? No problem. I'm going to use these values. If it was on a stack, we would have had to consume the values off the stack. We would have popped the 3 values off the stack to use them. In this case, even after we use them, those 3 values are still stored in those registers. We didn't overwrite them or anything. We might not need them again, but we still have values sitting in those registers. Okay, so we kind of see a description of the different registers things here. So A1 through A4, although they've called it R1 through, they actually called R0 through R3 is here. So, oh yeah, they're calling it for standard thing. This is mapping. So actually, we're going to focus on the left column here. Is that going to be good enough for us? Yeah, the far left column matches up to the text that we have up there. This is our R0 through R15 registers. So R0 through 3 is commonly used for arguments. R4 through 7 are for holding variable pieces of information. R8, R9, same thing. Again, we're dealing with conventions here up until we get to R13. So R0 through R12, this is just a, hey, it's probably a good idea to use those registers for these because that's what the operating systems assumed when they were written for that, and what the compilers kind of take into consideration. But when you, for instance, the homework that's due on Tuesday, where I'm just asking you to do, you know, some light things, just moving things into registers and stuff like that. I mean, they're all 32-bit registers. It frankly doesn't matter where you put them. Yeah, you got 16 registers to work with for you to swap 2 numbers, I think is what I'm having you do. You know, so it's you don't really need to follow conventions because you're not having to be compatible with some operating system. Okay. Let's let's see, ARM instructions. Nearly all of the possible instructions fall into the following three classes. They're either data operations. So these are arithmetic stuff, math stuff, or bit operations. We looked at bitwise stuff before. So they're memory operations. These are load and stores. So load and stores, when we load something, we're going to be bringing something from system memory onto the processor to store it into a register. A store is when we take something from our register and store it back to system memory. Loads can also be used to store immediate values, to load an immediate value into a register. Like you can load the value 27 into a register. So you're not actually sourcing it from system memory. You're just saying, hey, here's the literal integer value 27. I want to put it in R5, something like that. And then lastly, we have branches, and this is for loops and if statements and things like that, and function calls. Now, what's interesting here is, so, you know, for those of you who've never done assembly before, some of this might seem pretty cryptic, but remember this guy here? Remembering stuff, asking questions, repetition. Remembering stuff, asking questions, and repetition is covered right there. And then the data operations are, this is the stuff we might want to do to those. That's our logic. So effectively, we cover what any programming language is supposed to allow us to do through three fairly simple classifications of instructions. This stuff doesn't have to be difficult in order to do its job. It just seems a lot of people are immediately kind of intimidated by assembly. You know, at first glance, until I started walking through this, I'm sure that this code probably looked fairly intimidating to you. Stand it up here. You know, so if you've never had assembly before, or it's been a few minutes, you know, whatever your situation is, when you first glance at this little thing, it's intimidating. Like, this does not look like Java or Python or whatever modern day high level language I've dealt with. Okay, but once you dig in, you see we're actually doing something super simple. Why? Because every line of code here translates into exactly one instruction in the CPU, right? We are loading into this register this value. 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 So those first four lines there, all they're doing is moving values into four different registers. We're just remembering four things. And unless you know that there's going to be some operating system involved later that really cares about what those things mean and where you put those, you don't necessarily know the why you're putting those values in those four places. But when we look at the code, we know we are putting those values in those four places. Only here, when we actually tell the operating system to go and, you know, take a look, you know, I've set the table for you. Now it's time for dinner. You know, the table's set, and now the operating system can run in and start working with it. That's the point when you can understand the connections that the Linux operating system dictated on this Intel-based assembly. All right. So, and branches are used to like jump around the code. So, you know, we might have an if a certain Boolean thing is true, jumped 8 lines later, else jump 15 lines later, you know, whatever it is, that kind of thing. Actually, it would usually be, if it's true, go to the next line. If it's false, skip over the next 12 lines and move on with life. Loops are the same thing, except when you get to the bottom of it, it has to jump back up to where it used to be so it can test the operation again. Okay. This next line is so it says data instructions usually happen in a single cycle. Memory operations uses 2 or 3 cycles, and branches use 3 or 4 cycles. A cycle is you can think of it as like almost like a single RPM on the a single revolution on like an engine. You know, you have an engine that has 500 RPMs or something like that. So that means it does 500 things, 500 moves in a minute. So you can think of a cycle as a single move on the processor. So this is just giving us an idea of the cost of different instructions. So memory operations, well, let's see, data instructions happen quickly, memory happens a little bit more slowly, and branches happen even a little bit more slowly. It's saying it's more complicated than this, and I'm sure it's significantly more complicated than that, but that just gives us a kind of a pecking order of when you're, and this is the same thing that's true in high level programming. When you use if statements or loops, things like that, well, that's going to slow your program down more than when you just load something into a variable. That's a less time consuming operation. And typically your processors have a lot of your math stuff built into it. So those operations tend to be very quick. So when we do data stuff, this just gives us an idea of what's fast and what's slower, not overly important to us because this isn't a compiler's class. So, the idea of a compiler's class would be to say, okay, here's a high level program. When we compile this, it needs to produce something that looks like this. But not only do we want it to be assembly language like this that's accurate, it also needs to be as efficient as possible. Because one of the jobs of a compiler is to make a programmer look better than they were when they wrote it in the high level language. So we try to optimize your maybe poorly written but accurate high level program. But in here, we're not a compiler's class, so all we care about is, hey, does this assembly function? I've asked you to move a couple of things in there and swap some values using some other registers. No problem, just solve the puzzle. Doesn't matter how inefficient you go about solving it. Okay, all instructions are conditional. On most processors, you can only use branches conditionally, but on ARM systems, you can attach the conditionals to all instructions. This can be very handy for small if-else blocks. So for high-level programming, this would be like an inline if statement, or compound conditions, which would otherwise require the use of more time-consuming branches. So the code below contains, let's see, do we actually get to see the code? Yeah, we do. So the code below contains an assembly version of the familiar max function. So taking in two values, A and B, which one's bigger? The first one is the traditional version, which requires two labels, two jumps, actually, let's just look at it. That'll be better. Okay, so and again, this is not ARM assembly. This is Intel-based assembly. Actually, no, it's not. It's using ARM. So this is ARM assembly. So we are going to compare R0 and R1. So this is our traditional code. So this is using ARM to solve the problem without taking advantage of some of the ARM efficiencies. So this first thing, this is effectively an if statement. Okay, so we're going to compare R0 and R1 to each other. We're going to branch if less than. So if R0 is less than R1, we want to jump to this label right here. And we're going to move R1 into R2 because R1 is the higher values. Because remember, we're solving the problem of find the maximum value. Compare them. If R1 is the maximum value, move R1 into R2. Otherwise, if this was not true, if we didn't branch to less than, then we moved R0 into R2. So our final answer is sitting in R2. We either hit this line right here, where we moved R0 into R2, or we hit this line where we moved R1 into R2, depending on which of those two values was the larger value. All right, and this thing we're looking at right here, this is kind of the page that's going to help you with the homework assignment. All right, so following the logic we're doing here. Okay, so again, here's the function we're trying to solve here, and they even show it to you up here. R2 is going to be equal to the maximum value of R0, R1. That's what this code does. We compare the values, we branch if less than down to here. So if R0 was less than R1, put R1 into our answer, R2. Otherwise, if we didn't branch here, we move to the next line and we put R0 into R2 because it must have been the bigger value. And then we just bump into this next line. Our program counter started off here, then it went here, and it either went here or it went here, depending on what this branch did. Branches jump us around. All right. But then when we get here, this is a non-conditional branch. We're just saying, okay, one way or another, we have accomplished our task. one way or another, we've accomplished our task. So I need to branch down to this guy. And this is the rest of our code. But punchline is stored inside of R2 is the maximum value of R0 and R1. Okay. So that's what this code does in a fairly straightforward way, but not taking advantage of some of the efficiencies of ARM. All right, this is just traditional branch. Compare them, branch if one is the winner, else set the other one as the winner. Now using ARM instructions, we can, and this is where the, here, let me just show you the verbiage that it's saying. ARM systems, you can attach the conditionals to all instructions. So that, sorry, you know, this less than stuff, that can be attached to any instruction in ARM. So I'm going to compare R0, R1, and then I'm going to move into R2, R0, if it was greater than. Okay, so if R0 was greater than or equal to R1, move it into R2. This will only conditionally occur. So we might execute this line, but nothing may occur in that line. Because if R0 was not greater than or equal to R1, we would just not put anything into R2. The next thing, we're going to attach that conditional. So move if less than R1 into R2. So we're accomplishing the exact same logic here as we did up here, but we see how this is cleaner and we didn't actually have to do the real jumps. Now, behind the scenes, jumps are probably still occurring, but we didn't actually have to do the real jumps. All right, so let me pause here for a minute. Are there questions about this? I mean, what I want you to be feeling right now, especially if it's the first time you've ever seen assembly, is when you glance at this, it feels cryptic. But as I'm walking through it, you realize, oh, we're not really doing much here. We're just saying if this number is bigger than this number, put it in R2, otherwise put the other number in R2. That's all we're doing. So if anybody wants me to explain something else about what this code is doing, ask now, because I think this code is going to be very valuable for doing your homework assignment.
So, question. So you said, let me see. So would you recommend us doing the kind of code, like thinking about the code from another perspective and then maybe transferring it over to assembly, or would you say going into assembly, try to use the instructions from assembly and try to finish your assignment?
Well, I mean, those are the same thing. I mean, in this case, we thought about it in a high level, right? You know, we kind of imagined what is the max function likely to do. The max function takes in two parameters and it returns the maximum of those two parameters. So we've thought about it at this high level because that's easy for us to understand. And I think the homework assignment is something like load 3 values into some registers and then swap them in some way.
Yeah.
You know, so I mean, sure, I make sure you at least understand what I'm asking you to do. That would be the high level thing. You know, then you're going to write the instructions to accomplish it and the things you're going to be doing. I mean, you may not need to use any branches or anything. I mean, so don't necessarily feel like you have to do all of this. I would assume most of what you're going to be doing is moves. And then, maybe using, I mean, you have, 16 registers to work with. So, you can kind of spread out a lot. Like I said, you don't need to be efficient. You can just say, okay, well, I haven't used register 9 yet. So I'll just go ahead and throw this guy over register 9, because you're not having to worry about an operating system, wanting you to put something in R3 or something like that.
Right.
But yeah, so I mean, understand it at the high level, but then, don't try to get fancy. I just want you practicing with some assembly instructions to get a feel for kind of the how granular you need to make your moves.
Okay.
All right, other questions?
So, is there a particular software you recommend that we utilize to write the assembly code?
No, I mean, you can probably go to onlinegdb.com, and they probably have an ARM assembler on there. The problem is going to be is, because I'm not asking you to write a whole program, I'm just asking you to write kind of like, give me 6 or 7 instructions that accomplish some task. You're not going to be able to test it on there. So, really look at this as if it was like a test question, and I'm just saying, write some code that accomplishes something. So, I want you to be able to walk through it. So you can do this in any text editor or something. You're going to have a hard time testing it unless you go and embed it in an already working ARM program, which you can. I mean, let's just look here real quick. I'm not saying you can't do that. Online GDB. Let's see what assembly we have here. This is not, so this is going to be i386 assembly. Online assembler and disassembler. Oh, so this is interesting. Just if you ever see something that says the word thumb after it, ARM, the thumb version of ARM is like a cut down version of ARM. So get it? You have ARM and then you have the thumb. So that's where that comes from. So you could use ARM in here. The problem is that I don't think it's going to. I don't think you're going to get any output from it, since it's not a full working program. So you can write some code here that gets assembled into ARM. Yeah, I mean, you can mess around with some different things like this and see if you find one, but that's not the intention. The intention is for you to just write it by hand and trace through it by hand and figure out if it's doing what it should be doing. This is not going to be 200 lines of code. You're going to have like less than 10 lines of code to accomplish the task.
Okay, thank you.
All right, anything else? I'm going to look at this link here real quick, because I put this link here for a reason. Let's see if it's something good. I think this is just a ARM documentation I gave you. Yeah, so I'm still saying write it by hand. All right, so, but this is some documentation for ARM, so you might find this handy if you want to go and look up some instructions that are available and things like that, but I think, you know, what I've shown you probably will let you accomplish everything. Yeah, so we'll probably start here. Next time. All right, questions, comments, concerns, bribes?
A quick question, are you gonna upload those 2 videos for this week, the recorded videos for this class?
Yeah, the other one was not uploaded?
No,
Okay, yeah, I usually upload it right after class, so I'll upload both of them here in the next 20 minutes or so.
sounds good.
All right. All right, have a good one.
You as well, Professor Lippman.